We are on FRQ topic number 5, differential equations. So after this one, we'll be halfway done with our review of the FRQ types of questions. Looking at our most recent AP exams and where we saw this, we saw it 2019, 17, 16, 15, 13, 12. So they've missed a couple of years. Who knows, but there you go. So we do see it more than, say, area and volume, but maybe not quite as much as series, of course, and graphical analysis. All right? So grab your sheets and let's see what these can entail. We are going to start with the question from 2016. This is without a calculator. Most of these are with no calculator. I didn't mention that here, but most these are going to be no calculator questions because you're going to be solving a differential equation by hand. In part A of this question, they give us this differential equation. There's no meaning behind it. There's no, coffee brewing or, whatever. In part A, they just ask us to find the second derivative in terms of x and y. Second derivative. So we're taking the derivative with respect to x of dy dx. We're taking the derivative with respect to x of dy dx. So that means we're taking the derivative with respect to x of x squared minus 1/2 y, right? Take the derivative with respect to x on both sides. Well, the derivative with respect to x of x squared is just 2x. The derivative with respect to x of negative 1/2 y is, you first take the derivative with respect to y, that'll be a negative 1/2, and then you multiply that by dy dx. Little implicit differentiation, that's the chain rule. That is the chain rule there. They ask us to write this in terms of x and y, so all I have to do is replace dy dx with the x squared minus 1/2 y. And I found dy dx with respect, we found the second derivative in terms of x and y. So what did they score that as? They scored that just as 2 points for the second derivative in terms of x and y. I don't know if they split that up into 1 and 1, maybe, or whatever, but I'm pretty confident in saying if you did not write this dy dx here, you would not have gotten either point of those. All right, part B. Let y equals f of x be the particular solution to the given differential equation. By the way, this is not one where we cannot actually find y here. We cannot solve this differential equation because this is not separable. All right? So it says let y equals f of x be the particular solution whose graph passes through negative 2, 8. Does the graph of f have a relative min, max, or neither at negative 2, 8? All right. Well, my mind shifts back to what we did in function analysis. Relative min, relative max, or neither. I first consider the first derivative. So I'm looking for f prime at negative 2, right? I'm looking for f prime at negative 2, which is dy dx at my point, negative 2, 8. So I'm putting negative 2 in for x and 8 in for y, and I do get 0. That means maybe we have a relative min, maybe we have a relative max, maybe. Or maybe it's still neither, but since the first derivative is 0, there's a chance to be a relative min or a relative max. So we just now found the second derivative, so I think it would make sense for me just to use the second derivative. So the second derivative at that same point If I put negative 2 in for x, I'll have a negative 4 there, minus 1/2 times, and I just did that piece. That's my dy dx. Well, dy dx was 0. I just found that. So this is negative 4, which is negative. If the first derivative is 0 and the second derivative is negative, that means we have a relative max. So f has a relative max at the point negative 2, 8. Okay, so this was worth 2 points. 1 point, oh, I'm sorry, they gave us, it was all together. 2 points just for the conclusion. They said conclusion with justification. All right, part C. Let y equals g of x be the particular solution to the given differential equation with g of negative 1 is equal to 2. Find this limit. When I see a limit in a FRQ, I am totally expecting L'Hopital's rule. I may not get it, but that's what I'm expecting. I'm expecting to have to use L'Hopital's rule. Okay? So in my mind, I'm expecting that, and I know what I need to show. If it is a L'Hopital's rule in an FRQ, I have to show specific work. AP requires it. So let's see what we have here. G of x, we're going to negative 1, so g of negative 1, that's 2. 2 minus 2 is 0. So so far, I'm thinking L'Hopital's rule, because the numerator is 0. If I put negative 1 in for x in the denominator, I get 0 as well. So this will be a L'Hopital's rule. Here's what you have to show on an FRQ to use L'Hopital's rule. You need to say that the limit of the numerator is 0, and the limit of the denominator, x. I almost put an n. We got so used to doing n's last in our series unit. The limit of the denominator is also 0. Therefore, L'Hopital's rule applies. Okay. Now, you do not have to say, therefore, L'Hopital's rule applies. You don't have to say that. But you do have to say these two things. So therefore, the limit as x approaches negative 1 of what we want is equal to the limit as x goes to negative 1. Now here I'm applying L'Hopital's. You do not have to say the little LH there. I do that, but you don't have to do that. But this is where I'm applying L'Hopital's. So I'm taking the derivative of the numerator. The derivative of g of x is g prime of x. The derivative of negative 2 is 0. Common mistake, kids write negative 2 here. The derivative of a constant, remember, is 0. The derivative of the denominator, it's a little chain rule. So 2 times 3 is 6. And then I'll have x plus 1 to the first times the derivative of the inside, which in this case is just 1. So a little chain rule there. Okay. Now I put in negative 1 again. I'll have g prime at negative 1. Well, g prime at negative 1 is 2, right? G prime at negative 1 is 2. I'm sorry, g of negative 1 is 2, not g prime of negative 1. G prime of negative 1, we're using our differential equation. And I'm going to put, so I need to come off to the side and do that. So g prime at negative 1 will be dy dx at the point negative 1, 2, right? So I'm putting negative 1 in for x, and 2 in for y, This turns out to be 0. Well, that's not good. And then, if I put negative 1 in the denominator, I get 0 also. So we have to do another L'Hopital's rule. And if we do another L'Hopital's rule, I have to state a similar thing to this again. So the limit of the numerator is 0, and the limit of the denominator is 0. Therefore, we're using L'Hopital's again. So the limit as x approaches negative 1 of g prime of x over 6 times x plus 1 is equal to, and here comes my L'Hopital's, the derivative of the numerator is g double prime. The derivative of the denominator is just 6, right? This will be 6x plus 6. The derivative of 6x is 6. The derivative of 6 is 0. So I know I'm not going to have to use L'Hopital's again because I have 6 in the denominator. So g double prime at negative 1. I'm going to come off to the side again. G double prime at negative 1 is our second derivative at negative 1, 2. So I'm using my second derivative up here that we found. Where did we find it? We found it in part A. So this would be 2 times negative 1 minus 1/2 times dy dx at the same point, which was 0. So that's negative 2. So this will be negative 2 over 6, or negative 1/3. Okay? So this was worth 3 points. 2 of those points were for applying L'Hopital's rule appropriately. 1 of those points was for the answer. I have no idea if you had not shown these. I know if you had not shown these 2 steps, you would not have gotten those 2 points. I know that. My question is, could you have still gotten the answer point if you did not show these 2 steps? And I don't know the answer to that. My response is, show your work. Show your work. You know to do it, so do it. Is it worth the amount of money that you could potentially be getting? It definitely is. All right. Let y equals h of x be the particular solution with h of 0 is 2. Use Euler's method, starting with x equals 0, 2 steps equal size to approximate h of 1. So, little Euler's method thrown in here. So, all right, so we're starting at x is 0, we're going to x is 1 with 2 steps equal size, so delta x is 1/2. I always start there. I have my initial point. My initial point is 0, 2. And I want my slope. This is all just point slope. Euler's method is all just point slope. Tangent lines. So my slope at that point will be dy dx at that point. So I'm using my dy dx that they gave me. X is 0, y is 2. So I'll have 0 minus 1/2 times 2, that's a negative 1. Y minus the y value is my slope times my delta x. So y is 2 minus 1/2, which is 3/2. So I have my intermediate point. My intermediate point is 0 plus 1/2, that's my step up for my x, and then 3/2 for my y. Now I'm going to find the slope there. Dy dx at my new point is, I'm using my dy dx equation again, x squared is 1/4 minus half of y. So that is 1/4 minus 3/4, so negative 2/4, which is negative 1/2. Y minus the y value is equal to my new slope times my delta x. So y will be 3/2 minus 1/4. So h at 1 is approximately 3/2 minus 1/4, or 5/4. This was worth 2 points. 1 point for Euler's method with 2 steps. Your 2 steps must be clearly shown, and then 1 point for the approximation. So this was an interesting problem because we had a differential equation that we could not solve. It's not separable, so you cannot solve it. They had us find the second derivative. They had us answer a question about a particular solution and having a relative min-max or neither. They had us do a L'Hopital's limit, and they had us do an Euler's method. So lots going on here, lots of variety. You be ready for anything. Be ready for anything with these types of questions. The next problem that I'd like to do with you is the problem from 2011. So grab your problem from 2011. I'll turn to that page in my packet. Okay. At the beginning of 2010, a landfill contained 1,400 tons of solid waste. They're giving us an initial value. Okay? Something at time 0 is 1,400 tons. I don't know what variable yet. I'm going to keep reading. The function W models the total amount of solid waste at the landfill. So W at 0, waste at 0, is 1,400. Okay? Planners estimate that W will satisfy the differential equation. They give us a differential equation for the next 20 years. W is measured in tons, T is in years, since the start of 2010. Okay. Use the line tangent to the graph of W at time 0 to approximate the solid waste that the landfill contains at the end of 3 months. So time is 1/4. This is a one-step. It's a tangent line. Approximation is a one-step Euler's method problem. That's what it is. Tangent line approximation, one-step Euler's method problem. We want W at 1/4. We have W at 0. One step, so delta T will be 1/4. So I have my point. W at 0 is 1,400. The slope there will be dy dx, dw dt at 0, 1,400. So I'm putting 0 in for t and 1,400 in for w. Well, there's no t over here, but I can certainly put 1,400 in for w. So I could leave it like that. That would be, I'm okay leaving it like that. So our W at 1/4, that's what we're looking for, minus our starting W. So difference of W's will equal our slope times our delta T, 1/4. So W at 1/4 is, I'm just going to bring over our 1,400. And this would be a safe stop spot. And I'm kind of shocked that I didn't at least subtract 1,400 minus 300, but I wanted to show you, I wanted just to show you that we don't have to simplify anything here. This is a no calculator problem, and like I said, most of these will be no calculator problems, these differential equation ones. Okay, part B. Find the second derivative in terms of W. Well, here is dw dt. I'm leaving a space right here because I know I'm going to be taking the derivative with respect to t of both sides. So I'm leaving a space here. So I'm taking the derivative of both sides with respect to t to get the second derivative. Why with respect to t? Because they told me with respect to t. So the second derivative of w with respect to t will be, all right, we need to use a chain rule here because I have w and I'm taking it with respect to t. So first I take the derivative with respect to w. Well, that derivative will just be 1 over 25. Because if I distribute this, the 1/25 times 300, when we take the derivative, will just be 0. So that's just 1/25 times dw dt, little chain rule. Derivative with respect to w times dw dt. In terms of w, they almost always will say that, so just in place of dw dt, put what dw dt is. So this will be 1/25 times 1/25 w minus 300. And now we want to use the second derivative to determine whether our answer to part A is an underestimate or an overestimate of the solid waste that the landfill contains at time 1/4. Okay, so we used the point 0.1400. So what I'd like to do is find the concavity right here. The second derivative is going to give me the concavity. So I'm going to say at the point 0.1400, the second derivative is 1 over 25 squared, 1400 minus 300, which is positive, right? That's positive. So our graph is concave up. If our graph is concave up, and this is one of those things where I don't want you to start writing too much. Do not write too much. But if the second derivative is positive, and we used a tangent line to approximate another point, think about that. We had a concave up curve, and we used a tangent line to approximate the next value. Now, whether our tangent line was here, or here, or here, the tangent line is always below the curve. Always. So if our curve is concave up, a tangent line will yield an underestimate. So I'm just going to say the second derivative is positive, therefore a tangent line approximation yields an underestimate. You do not have to say that the curve is concave up. Saying that the second derivative is positive is sufficient. It's not wrong to say that the curve is concave up there, but I always encourage you to be as succinct, as abbreviated as possible. Okay? This was worth 2 points. 1 point for the second derivative. Whoops. 1 point for an underestimate with reason. Okay, I forgot to give you guys the points up here. This was worth 2 points as well. 1 point for dw dt at t equals 0. So 1 point if you used, 1 point for finding dw dt at time 0, and then 1 point for our answer, the approximation. Okay. So far only 2 points out of the 9 have been awarded, so that means we're going to have 5 points for this part. Find the particular solution. These are always worth big points. Find the particular solution to this differential equation with initial condition given. So big points here, and that's good because I know this is something you can do. And our mantra here is separate and integrate. Separate and integrate. So dw dt is 1/25 W minus 300. You may or may not recall we do not distribute here. It's easier just to leave the 1/25 here, divide both sides by your W minus 300. So I'm dividing both sides by W minus 300, and I'm multiplying both sides by dt, the differential of t. I separated, now we integrate. The integral of this is natural log absolute value W minus 300. No coefficient because the derivative of this is positive 1. Remember, if the derivative of this is some other number, then you have to divide by that number out in front. 1 over that number out in front. There would be a plus c, but I'm going to combine the c's over on the right-hand side. This will be 1/25 t plus c. Okay. At any point after you integrate, we can use our initial condition. So I could use the initial condition here, and it wouldn't be wrong, but I think I'm going to e to both sides. If I e to both sides, I can lose the absolute values because of how I'm going to write this answer over here. When we e to both sides, we're going to get c e to the 1/25 t, where recall, this c is now no longer the same value as that c. These are two different constants, but they are both still constants. So I'm just going to call it a c. At this point, I am going to plug in my initial condition. So W at 0 is 1400. I'm communicating to AP what we're doing. I put 1400 in for W, and I put 0 in for T. 0 in for T, so this is just going to be e to the 0 or 1. So C is 1100, and W minus 300 is 1100 e to the 1/25 t. So W is equal to 1100 e to the 1/25 t plus 300. If you like, you can call that W of t, but it's obvious that it's a function of t from how we wrote the answer. This was worth 5 points. Let's see how they split that up. 1 point for separation of variables. 1 point for the two antiderivatives. 1 point for using a constant of integration, C. 1 point for uses our initial condition. And then 1 point for solving for W. With a little note, a maximum of 2 out of 5 points if no constant of integration, no plus C. If you forgot your plus C, at most you would get 2 out of the 5 points possible. Note, no points if no separation of variables. If you don't separate variables, no points. You've got to do that. So this is worth big points. I know you can get big points on this. You just have to do it. All right? Okay, on to the next problem. All right, next I would like to do the problem from 2019. This was number 4, no calculator. And I did give you this question. I believe I gave it to you on a test before. It's been a little while though, but I'm thinking it was on a test, either a test or a worksheet. A cylindrical barrel with a diameter of 2 feet contains collected rainwater as shown on the figure. Water drains out through a valve. The rate of change of the height of the water in the barrel is modeled by this differential equation. H is in feet, T is in seconds. And then they give us a formula for the volume of the cylinder. Okay, Part A, find the rate of change of the volume with respect to time when the height of the water is 4 feet. Little related rates question. And we don't mind related rates questions. We truly don't mind these. We have our formula for volume. And I know in a related rates question we need to take d dt of both sides. That's what we do. Now, that is all we do, but over here I have two variables, which means either I do the product rule. If I have to, I will do the product rule, or I ask myself, is there a way to simplify this and change it so that we only have one variable? Sometimes you have to use the product rule, but in this case, the radius of a cylinder is a constant throughout the entire cylinder. They give me that the diameter is 2 feet, so I know that the radius is 1 feet. So the radius is 1 foot throughout this entire problem. So in place of every r, I'm going to put a 1. So v is equal to pi times h. I left myself a space because I'm about to take the derivative with respect to t. Related rates problems truly are not bad. They really are not. So I get dv dt is equal to, all right, the derivative of this with respect to t, little chain rule. So first take the derivative with respect to h, that would just be pi, and then we multiply by dh dt, chain rule. Implicit differentiation is just chain rule. Okay. Now we need to put 4 feet in for h, so dv dt at h is equal to 4 feet, or you can say when h is 4 feet, that's fine, is pi times, now dh dt they gave me was -1/10 square root of h, and I'm just putting 4 in for h. They did not require, did they require units? Oh, they did require units. I almost forgot units. That's why I bubbled that. So units here, remember that we have d8, the units of h, it's units of volume divided by units of time, right? Units of volume over units of time. Well, units of volume here would be feet cubed. Units of time is seconds, so this would be cubic feet per second. Okay? All right. That was worth just 2 points. 1 point for writing dv dt is pi dh dt, and 1 point for the answer with units. So if you didn't write units, you didn't get your point for the answer, even if your answer was good. All right, part B. When the height of the water is 3 feet, when the height is 3 feet, is the rate of change of the height of the water with respect to time, that would be my dh dt, increasing or decreasing? So is dh dt increasing or decreasing? Well, if I'm trying to determine if any function is increasing or decreasing at a specific time or whatever, I take its derivative. So I'm trying to figure out if this is increasing or decreasing, so I need the derivative of that. So dh dt they gave me is -1/10 square root of h. I need to take the derivative of that with respect to time. To see if this is increasing or decreasing. So I will get the second derivative. And with respect to time here, this will be, this is h to the 1/2. So this will be -1/20, because 1/2 times 1/10 is 1/20. H to the -1/2 I'm going to put that in the bottom, h to the negative 1/2. That's the derivative with respect to h. Now we, little chain rule, multiply by dh dt. So we get negative 1 over 20 square root of h times dh dt is negative 1/10 square root of h. The square root of h's cancel out, don't they? And so I get that the second derivative is equal to a positive 1 over 200. Always. Not just when the height is 3, but always, right? So this is for all values of h. So this is the second derivative is positive, therefore dh dt is increasing when h equals 3, and for all heights, but specifically when they asked for h is 3, so I told them when h is 3. How'd they score this? It was worth 3 points, and it was 1 point for the derivative with respect to h of that piece. So just for this piece here, that was worth a point. And then 1 point for the second derivative being equal to, oh, my orange is leaving. I will go to pink. Is equal to negative 1 over 20 square root of h times dh dt. So that was what we had right here. So they focus in on that chain rule part. They'd like to see that chain rule. And then 1 point for your answer with explanation. Okay, part C. At time 0, the height of the water is 5 feet. Use separation of variables to find an expression for h in terms of t. Separate and integrate. They're telling you, separate and integrate. So d8, I'm pulling out our differential equation. And again, I know when I'm separating and integrating, I know these are worth big points. Now, we've already allotted 5 points up here, so this will be worth 4 points. Still a lot of points. So I'm going to separate and integrate. I'm going to divide both sides by square root of h. Multiply both sides by my dt. I separated, and now I integrate. So I'm thinking of this as h to the negative 1/2. Thinking of that as h to the negative 1/2. If you want to write it, write it. It's worth it, you guys. You don't want to make mistakes on here. So write it down if you need to. So now I'm applying the power rule. So this will be h to the positive 1/2 times 2 plus c, which I will combine with the other c. This will be negative 1/10 t plus c. Okay. Now I'm going to multiply both sides by a half. Multiply both sides by half. So on this side I'm going to have square root of h. On this side I'm going to have a negative 1 over 20t plus half of c is just another constant, right? I think that this is probably a nice time to plug in. So I'm plugging in the point 0 seconds, 5 feet. So 5 for h, 0 for time. So square root of 5 is 0 plus c. So square root of h is negative 120 over, times t plus the square root of 5. Solve for h because they ask us to find h. So h, we're squaring both sides. And that's our value, our equation for h. This was worth 4 points. 1 point for separation of variables. 1 point for the antiderivatives. 1 point for the constant of integration, and uses the initial condition. And then 1 point for your function for h. So separate the variables, that's where the point. Our two antiderivatives were worth a point. Using a constant and finding the constant, using the initial condition to find the constant, that was worth that point. And then our answer. 4 points, and I know you guys can do that. So I always like it. This year when the kids came back in and said they had to do a separation of variables, I thought that's good, because I know you guys could do that. I will tell you that since I have the information from back from 2019, I don't have information from a lot of years, but I have it from 2018 and on. The global average for this problem was a 3.6. 3.6. The KHS average for this problem was a 4.0. Okay, so think about that. Could you have gotten more than that in this problem? If you did this part right, that's 4 points on its own. Could you have gotten a point here or there for anything else? I'm hoping you could. I think you can. Now, it was number 4 on the FRQ. This is about on hour 3 of the exam. You're going to start to get tired, so you have to somehow find a way to stay fresh. Okay, so time to go practice, and let me know what questions you have.